Hello children, before we talk about potential energy, let us see conservative and non-conservative forces. We can divide internal forces of a system into two categories, conservative and non-conservative forces. We can define them in two ways. One, if the work done by a force during a round trip of a system is always zero, the force is said to be conservative, otherwise non-conservative. And second, if the work done by a force depends only on the initial and final states and not on the path taken, then the force is called as conservative, otherwise non-conservative. For example, gravitational force, electrostatic force and spring force are conservative forces, as the work done by them during a round trip of a system is always zero, whereas friction force and viscous drag of a fluid are non-conservative forces, as the work done by them during a round trip of a system is negative, not zero. A conservative force is a function of position only, not velocity or time, whereas a non-conservative force is a function of velocity. It acts in the opposite direction of the velocity. Now let us talk about potential energy. In our previous classes, we have studied that the energy possessed by a body by the virtue of its position in a system relative to others is called potential energy. An object's potential energy depends on its physical properties and the position in a system. As we had started kinetic energy with change in kinetic energy, we will start potential energy with change in potential energy. We consider internal forces and external forces working on a system. Internal forces are divided into two categories, conservative forces and non-conservative forces. Corresponding to each conservative force, we associate potential energy, but we cannot associate potential energy corresponding to non-conservative forces. We associate kinetic energy with the external forces. So we define the change in potential energy of a system corresponding to a conservative internal force as UF minus UI is equal to minus W, or delta U is equal to minus W. Potential energy is represented by capital U. Here W is the work done by the internal forces on the system as the system passes from the initial configuration I to final configuration F. You need to remember this formula. Suppose only conservative internal forces work between the parts of a system and the potential energy U is defined corresponding to these forces. There are no external forces or the work done by them is equal to zero. That means these are the conditions. Conservative forces work, non-conservative forces do not work. External forces do not work, or even if they work, sum of work done by them is equal to 0. Then we can say UF minus UI is equal to minus W. That means change in potential energy is equal to negative of work done. From work energy theorem, replace W by Kf minus Ki. So UF plus Kf is equal to UI plus Ki. Sum of kinetic energy and potential energy is known as total mechanical energy of the system. From this equation, total mechanical energy final is equal to total mechanical energy initial. That means total mechanical energy of a system remains constant if these conditions are met by the system. This is known as principle of conservation of energy. In other words, we can apply principle of conservation of energy when system meets these conditions. The total mechanical energy K plus U is not constant if the non-conservative forces such as friction acts between the parts of the system. We cannot apply principle of conservation of energy in the presence of non-conservative forces. That means if this is strict, we cannot apply principle of conservation of energy. However, work energy theorem is still valid in the presence of non-conservative forces. As per work energy theorem, work done by all the forces, internal as well as external forces, equals the change in the kinetic energy of the system. That means WC plus WNC plus W external is equal to Kf minus Ki. Here WC means work done by conservative forces. WNC means work done by non-conservative forces. W external is work done by external forces. Kf is final kinetic energy of the system and Ki is initial kinetic energy of the system. Put Wc is equal to minus Uf minus Ui. We know that Uf minus Ui is equal to minus Wc. Change in potential energy of the system is equal to negative of work done by conservative forces. So putting this value of Wc in this equation, we get Wnc plus W external is equal to Ef minus Ei. That means work done by non-conservative forces plus work done by external forces is equal to final mechanical energy of the system minus initial mechanical energy of the system. Now consider these conditions. Conservative forces work, non-conservative forces do not work, external forces work, and sum of work done by them is non-zero. Then Wnc is equal to 0 or W external is equal to Ef minus Ei. That means work done by the external forces equals the change in mechanical energy of the system. Now let us see gravitational potential energy. Suppose a block of mass m is kept on the ground. Then it is raised vertically upwards through a height h. We can consider the block and earth as a system. Gravitational force working between the block and earth is conservative. So we can associate a potential energy corresponding to this force. Gravitational force on the block is working vertically downwards and it is raised vertically upwards. So work done by the gravitational force will be negative and it is given by W is equal to minus force into displacement. Force is equal to mg and displacement is h. So W is equal to minus mgh. Change in potential energy of the block earth system is equal to negative of work done by the conservative force. Put W is equal to minus mgh. So delta U is equal to plus mgh. That is, potential energy of block earth system in this case will increase. Similarly, if the block descends through a height h, work done will be positive and change in potential energy will be negative. That is, potential energy of block earth system in this case will decrease. Now let us see potential energy of a compressed or extended spring. Suppose one end of a massless spring is attached to the wall and other end is connected to a block of mass m. Now this block is pulled towards right through a distance x, so that the spring is elongated by a length x. Now in this situation, the spring will pull the wall towards right and pull the block towards left. As a reaction force, wall will pull the spring towards left and block will pull the spring towards right. These two are external forces. Work done by this force is equal to 0 because the point of application of force is fixed, and work done by this force is equal to integration of kx dx from 0 to x, and that is equal to 1 by 2 kx square. So total work done on the spring by external forces is equal to 1 by 2 kx square. This work done is positive as the force acting on the spring is towards right and elongation of the spring is also towards right. So total work done on the spring will be positive and it is 1 by 2 kx square. We know that total external work done on a system is equal to the change in its total mechanical energy. And total mechanical energy of the spring is its kinetic energy plus potential energy. Since spring is massless, so kinetic energy of the spring will remain 0 all the time. So total external work done on the spring will be equal to its change in potential energy. So potential energy of the spring will increase by 1 by 2 kx square. Now suppose the potential energy of a spring in its natural length is 0. So potential energy of the spring will increase by 1 by 2 kx square when it is elongated or compressed by a distance x. Now let us understand potential energy and the nature of equilibrium. Suppose a particle's position and its potential energy graph is given. We know that change in potential energy is equal to negative of work done by the conservative forces. So we can write du is equal to minus fdr or f is equal to minus du by dr. That means conservative force is equal to negative of slope of the curve. There are 3 points of interest: point P, point Q, and region Rs. Point P where potential energy is minimum, point Q where potential energy is maximum, and region Rs where potential energy is constant. At points P and Q and in the region Rs, slope of the curve is 0. That means conservative force is equal to 0. Particle will be in the state of equilibrium. There are 3 types of equilibrium: stable, unstable, and neutral equilibrium. Let us understand them one by one. First one is stable equilibrium. It corresponds to the point where potential energy is minimum. Suppose the particle is at point P. If it is displaced a little bit towards left or towards right, it will keep oscillating about point P till it settles down at P again. This part of the curve is known as potential well. Also, at the location of stable equilibrium, F is equal to minus du by dr is equal to 0, df by dr is less than 0, and d square u upon dr square is greater than 0. Second one is unstable equilibrium. It corresponds to the point where potential energy is maximum. Suppose the particle is at point Q. If it is displaced a little bit towards left or towards right, it will never attain the same position Q again. So it is in the state of unstable equilibrium. At the location of unstable equilibrium, F is equal to minus du by dr is equal to 0, df by dr is greater than 0, and d square u upon dr square is less than 0. Third one is neutral equilibrium. It corresponds to the region where potential energy is constant and force is 0 everywhere. So this is the region where potential energy is constant and this is the region where force is 0. In the region of neutral equilibrium, F is equal to minus du by dr is equal to 0, df by dr is equal to 0, and d square u upon dr square is equal to 0. Now let us talk about power. The rate of doing work is called power delivered. We know that work done by a force F in a small displacement dr is given by the formula dw is equal to F dot dr. So power delivered by the force will be dw by dt, and that is represented by letter capital P. From here dw by dt is equal to F dot dr by dt, and dr by dt is equal to velocity v, because rate of change of displacement is velocity. So power P is equal to F dot v. The SI unit of power is joules per second and it is written as watt. A commonly used unit of power is horsepower. 1 horsepower is equal to 746 watt. In next video, we will solve few numericals based on what we have studied so far in this chapter. If you have a question, you can ask me on my Discord server. If you have not subscribed my channel yet, please do so.